All right, type 6, differential equations. And for you BC folks, Euler's method is also included in this review packet. All right, number 4, it does say BC, but this is one, except for part D, that an AB student might be asked to do. Part A is giving you, or you're asked to find the second derivative in terms of x and y. We're given the first derivative as x squared minus 1/2 y. So differentiating both sides to get the second derivative, we have 2x minus 1/2 dy dx. And we need to replace the dy dx with the given dy dx in the stem of the problem. You don't need to simplify, you can just leave it like that. All right, part B tells you that y equals f of x is a particular solution, and it goes through the point -2, 8, which is our x comma y, and we are asked whether the graph has a relative min, max, or neither at that point. So we're going to first plug it into the first derivative to determine whether it is even a candidate for a relative extrema. And so I plug in the value -2 for x and 8 for y. I do get 0, and so we know it's a critical point. And then we're going to plug it into the second derivative, which we got in part A. We find that that is less than 0 at the point -2, 8, which implies that we have a curve that's concave down at this critical point, which tells us we have a relative maximum. Part C is asking us to find the limit as x approaches -1 of this ratio of functions here. Well, over here on the right, I've done a little chicken scratch. The numerator, as x approaches -1, when I plug in -1 into the numerator, I get 0 for the numerator, and lo and behold, I get also 0 in the denominator. So now we can apply L'Hopital's rule. Remember, don't ever write 0 over 0. You can just look at the behavior of the numerator and denominator. So I'm going to take the derivative of the numerator divided by the derivative of the denominator, and again, I'm going to look at what those values are. And so in the red, we have the behavior of the numerator and denominator at our new functions g prime and 6 times x plus 1. Both of those, again, are equal to 0. We can apply L'Hopital's rule. I get g double prime over 6. Remember, g double prime from part A, and then we're going to plug in the value that was given way up here at above. We're given -2, 2. We plug that in. I get -2, and I get -2 as a second derivative of g over 6, and I get -1/3. All right, this is a BC only topic for Euler's method, so AB students would not ask to be doing this. Again, we're still using the same dy dx that we were given in the stem of the problem. Euler's method, I find the most easiest way is the chart, where you have x, y, dy dx, delta x. Your delta y is dx times dy dx. Your new y is your old y plus your delta y. And so we're given 0, 2 is my initial point. We're asked to find the value h of 1. And so we're going to just go through this chart. Be very careful. I did a little chicken scratch right here to get to the -1/2 for my dy dx in my second my second step there. And our approximation is h of 1 is 5/4. All right, 2017 AB. A lot of writing here, or a lot of written words, but just be careful as you read through it. Make sure that you note the initial time and what the temperature is. So we have this rate of change of our temperature is -1/4 H minus 27. Also in the stem of the problem, it tells us this H is always greater than 27 degrees. That will be helpful later on. First part A is asking you to write the equation of a tangent line. So again, I just do my point slope form right here. And then I'm going to plug those in with my H, H1, T, and T1. I have my initial point, 0, 91. So I'm going to plug that in for T1 and H1 to find the slope At 0.91, I'm going to plug that into my given differential equation, negative 1/4 h minus 27. So I did that right over here in the chicken scratch. I find that my slope is negative 16. Rearranging it, I have now an equation for my temperature, and then I want to approximate it when the time is equal to 3. And so I'm going to put 3 in for t in my equation. You don't need to simplify this. If you don't have a calculator, just leave it as 91 minus 16 times 3, but that value is 43. Part B of this problem is to use the second derivative and to determine whether your answer in part A is an under or an overestimate. Taking the second derivative of our given dh dt gives us negative 1/4 times the derivative of h with respect to t. I'm going to plug in the original differential equation into our second derivative and then clean it up just a little bit. However, remember, we know that h is always greater than 27 degrees, and so this value h minus 27 will always be positive, and therefore the whole entire second derivative is positive, which implies that our curve is concave up, and any tangent line lies below the curve and therefore is an underestimate. So I just gave you a little diagram right there. All right, part C is a very important skill for both AB and BC students. It's called solving by separation of variables. And so I'm given my differential equation dg dt, and I'm just going to put a little negative 1 right there in front. The first step 1 is to separate your variables, meaning anything with a g goes over here on the left-hand side, anything with a t or your constant's going to stay on the right. Okay, so that's step 1. Step 2 is to integrate both sides, and obviously don't forget your plus c right here. You don't want to forget that. So I'm going to integrate both sides. I'm going to make sure I remember to do plus c. Step 3 is you're solving for c given your initial value. In this case, it's 0.91. So I'm going to plug in 0 for t and 91 for our g. And then I solve for c, which c is 12 there. Our very last step is to actually solve for our function. In this case, it's g. And so I'm just going to put my c that we just found in there. I'm going to divide both sides by 3. And then I'm also going to cube each side, and I'm going to slide that 27 over on the right. So here is my function in terms of g. I'm going to let t equals 3 because they asked for g of 3 in part C, and I get 27 plus 27. And you can leave it like that. All right, 2016 number 4 for AB. You are actually here constructing a slope field. I would strongly suggest first doing a little table with all the values of only the points that are listed in the little given diagram or graph. If you notice that from our given differential equation, y squared over x minus 1, where we have an undefined slope at x equals 1, don't put anything. I know Delta Math has putting a vertical line when your slope is undefined. However, on the AP exam, do not put slopes or any kind of little tangent line or slope line when you have an undefined value. So when x is 0 and y is 0, we get a slope of 0. At 0, 1, we have a little negative 1. And at 0, 2, we have negative 4. Just make it steeper than negative 1. At 2, 0, we have a slope of 0 again. At 2, 1, we have a slope of 1. And at 2, 2, we have a slope of 4. So just make it steep. Part B was asking you to write the equation of a tangent line and then use that to approximate your value f of 2.1. So again, my point slope form, I rewrote it in terms of our given function f, and we know the point that we're given is 2, 3. So I know f of 2 is 3. My slope, I use y squared over x minus 1. My slope at the point 2, 3, plugging that in, I get a slope of 9. Okay, so here's my y value, here's my slope, and here's my x value. To approximate f of 2.1, we're going to plug in 2.1 for x, simplify, and we get 3.9. Part C, again, is solving this differential equation. We have our 3 steps. Step 1, separation of variables. Step 2, you want to integrate both sides, and don't forget the plus c. Step 3 is you're going to solve for your particular c And step 4, in this case, you're going to solve for your equation, and this is in terms of y equals. All right, here, 2015, this is a BC problem, but again, there are lots of AB parts that the AB students are going to be required to know. So the first thing is, in part A, is to construct a slope field. Again, I would suggest the table. So at 0, -1, we have a slope of 1. At 0, 1, I have a slope of -1. At 0, 2, I have a slope of -2, so just make that a little steeper. At 1, -1, I have a slope of 3, which is kind of steep. At 1, 1, we have a slope of 1. And at 1, 2, we have a slope of 0. Part B is asking you for the second derivative and then determining the concavity for any point in quadrant 2. So the second derivative, again, is just going to take the first derivative and differentiate with respect to x. So I get 2 minus dy dx. I'm going to plug in the original dy dx from the stem of the problem and simplify if needed. Now, in quarter 2, we know some information about x and y. X is always less than 0, meaning it's negative. Y is always greater than 0, which means over here in my second derivative, a -2 times a negative number is also going to be then positive, and we're going to have the sum then of a bunch of positive numbers. So we know that the second derivative is always positive, and so the solutions, or the solution curves in the second quadrant, are going to be concave up because our second derivative is positive. All right, part C asks at the point f of 2, 3 or 2, 3 do we have a max, min, or neither? And so putting that ordered pair 2, 3 into our first derivative or our differential equation, we actually get a value that's not equal to 0. And therefore f of x has neither a max or a min at x equals 2 because 2, 3 is not a critical point. All right, part D, a little tricky, but great problem, and these are the types of problems you're going to see more often than not in the current AP exams. So we're given that y equals mx plus b is actually a solution to our differential equation, which is given in the stem of the problem right here. So taking the derivative of that given solution, I get dy dx is equal to m. But I also know from the stem of the problem that dy dx is equal to 2x minus y. So I can set m equal to 2x minus y. But I also already know what y is. It was given to be mx plus b. So I put that in the equation, clean it up a little bit in the second line, and then I'm going to factor an x out of these first two terms on the right. Now, I don't have any x terms on the left, so I'm going to add this 0x plus m. Doesn't change the equation. Now, I know that that 0 times x has to equal the 2 minus m times x. So 0 has to be 2 minus m, and m is 2. That also means that this m right here is going to equal negative b. And since negative m equals b, then b is going to be the opposite of m, which is positive 2. That's one way to do it. Another way to think about it is if we're given this y equals mx plus b, we know y prime is the same thing as dy dx, which in this case is 2x minus y in the stem of the problem. My second derivative, okay, we've already done this before, is 2 minus the quantity 2x minus y. But I also know my solution, y equals mx plus b, is a linear function. And we know that of every linear function, the second derivative is always equal to 0. So I'm going to set that 0 to that second derivative I got, clean it up, and I get y equals 2 minus 2x. But I know y is mx plus b. So if y equals 2 minus 2x, my m has to be negative 2, and my b has to be 2. All right, last free response question in this type 6 differential equations. In this problem, we're given our first derivative, or our differential equation, dy dx equals y squared times the quantity 2x plus 2. I also know I have an initial point, 0, negative 1. Part A is asking us for a limit, and so we're going to look at the behavior of both the numerator and denominator as this x approaches 0. Our numerator is f of 0 plus 1, but I know f of 0 is negative 1, so I get negative 1 plus 1, or 0. Sine of 0 is also 0, which allows me to use the L'Hopital's rule, taking the derivative of the numerator divided by the derivative of the denominator. I already know what f prime is. F prime is our differential equation, x squared times 2x plus 2. And plugging in our initial point, 0, negative 1, into my f prime, that gives us a value of 2 divided by the cosine of 0, which is 1, so I get a positive 2. Part B is Euler's method. Again, this is a BC only topic, but again, BC students are expected to know how to do this. So I'm going to do my chart with my xy, my dy dx, my delta x. If I'm going from 0 to 1/2 with 2 steps, my delta x is going to be a fourth each time. My delta y is delta x times dy dx, my derivative or my differential equation at the given values, and then my y new is my y old plus my delta y. Okay, I did a little chicken scratch over here to find that second dy dx, and there you go, which is 5/8. Be careful of your algebra. You can leave your final answer in -1/2 plus 5/32, or simplify it to -11/32. In part C, this is both an AB and a BC topic, solving for the particular solution. Remember, step 1 is separation of variables. Step 2 is to integrate. Don't forget the plus C when you integrate. Step 3 is to solve for C using your initial value or point. In this case, we have 0, -1. And step 4 is to solve for Y. All right, and multiple choice questions. There's 3 of them in this review packet for type 6. Question 23 asks, which of the following differential equations describes linear growth in the size of population? Recalling that linear growth, the derivative has to be constant if the function is linear. We only have one differential equation in those 5 choices that is a linear differential equation, which means it's 200. Remember, differential equation is the same thing as the derivative. Number 25, I'm actually solving. Again, remember your steps, separate your variables, integrate both sides, remember the plus C, solve for C, and then solve for Y. And my steps are here, and that answer would be choice E. All right, this one's a tad bit tricky. We're giving 2 points that are on my function. And then we're also given our differential equation, dy dx equals x squared plus y. So I'm just sort of going to go through these choices. Choice A says at the point 1, -5, what's going on? So I'm going to plug 1, -5 into my differential equation. Remember, that's the first derivative. I don't get 0. Okay, and since I don't get 0, then the point 1, -5 cannot be considered for a relative extrema, and choice A is false. So in part B, it talks about a point of inflection. So I've got to find the second derivative. So I did the work here for the second derivative. Remember, I plugged in the original dy dx into the dy dx in the second derivative. Again, I plug in the point 1, -5. I don't get 0. And therefore 1, -5 is not a candidate for a point of inflection, and choice B is also false. All right, at -1, -1, I plug in that point into my given differential equation. Remember, that's the first derivative. I do indeed get 0. So now we have a candidate for a relative extrema. Then I plug that into the second derivative, which I found in choice B, and I find that that's less than 0, which tells me we're concave down, which tells me that I have a relative max. And if choice C is correct, choice D and choice E are also false. Well, choice C is true, so D and E are false.